Okay, welcome to class, everybody. Oof, it's loud. Thanks to the brave souls that came despite it being Thanksgiving tomorrow. Delighted that you guys came today. Our learning objectives are the following. First off, I'm going to give you a tip for taking tests that, in talking with a few students, I think might really help people out. We're going to get into band diagrams, which is really an interesting concept, and it's why some materials like ceramics just don't conduct electricity, but metals do, and semiconductors are somewhere in the middle. There's a really interesting sort of graphical way to understand that, and it's called band diagrams. Once we understand that, we'll be able to do things like understand where the electron level lies in these bands, and that tells us all about semiconductors, intrinsic versus extrinsic, so we'll get into those topics. I hope that we'll be able to describe how the conductivity changes in a metal when you change the temperature, and how that's different than a semiconductor. And if we have time, we're going to get into some basic devices, but more than likely that'll be on next Monday. So let's start with partial credit and how to maximize your time on tests. So I've had a lot of people come in and say, like, oh, I feel like I'm understanding the homework well, I'm getting good scores. Then the test rolls around and I either panic because, like, I'm worried about time, or I feel like I know it and then I just don't, and I don't know how to get the most partial credit. We really try and not penalize students if you just make a math error. If you make a math error early on in the problem and you propagate that, that's like a -1. That's no big deal. So in talking to these students, I think that it would be helpful to describe it to everybody. When you face a problem, really, if I were you, the very first thing I would do is go in reverse, right? So let's assume this is the problem. It says, you know, if copper is initially at room temperature, what would be the final temperature if copper has such and such a specific heat, such and such a density, and then I say give the answer in degrees Celsius, rounded to the nearest hundredth of degree. The way that I think you can maximize your partial credit is to do this problem in reverse. Say to yourself, okay, I'm being asked to figure out the final temperature. So to get temperature final, right, what do you need? So think the next step back. In this problem, assuming that we did the problem, remember this picked up from last class. Last class we figured out how much energy is generated when you pass current through this metal with a certain volume dimensions. We figured out how much energy was generated, right? So Q, the very last thing that we did is we could have plugged this in, and I think we said it was 188 millijoules. I think that's what it was. We can double check in a minute, right? So we had energy. So this problem takes it a step further and says, okay, from that energy, how do you figure out a final temperature, right? So to get to our final temperature, we're going to have to go from our temperature initial to get to our final temperature. That means we're going to have to solve for a delta T, right? Right, to do that. Well, how do we get our delta T? Delta T can be figured out from heat capacity, from our heat capacity equation, right? We know that Cp equals the amount of, the energy, right? So Q divided by the amount of material. So this is mass of your material multiplied by the change in temperature, right? So it's that. So if you just sketch us just a really rough diagram of what's the flow of this problem, like we started out with Q, right? This was given from the previous problem, right? Cp is given. You need to get mass, and so if you just say, like, to get mass, we know that volume, to get to mass, we're going to use density, right? Just a diagram like this will get you the vast majority of your points. Without doing any calculations, this will get you at least half the points on a problem, and it will make sure that you don't do things that aren't getting towards the final product. Like, sometimes people just start, like, calculating. They're like, oh, I don't know what to do. And they just start, like, punching numbers in their calculator. Like, having a flow diagram like this of, like, what you need to do, starting with the end and working backwards to the information that you're given, it's just a suggestion, but I think it's a useful one, okay? And how do I know this works? Like, if you look at our tests, right? So this is all posted. You can see this, right? On this problem, this was a Weibull modulus problem. We asked you how many times larger should something be, right? The effective area, in order to have the same failure rate for these two different materials, right? So if you look at how we assigned points on this, 2 points were just for solving for y, right? We gave you a failure rate, 25%. Just going from failure rate 25% solving for y, 2 points, right? Then you got 2 points just for remembering that x is actually the natural log of your stress, right? You can't just solve for x. You then have to turn that into a stress by taking e of that number, right? For actually solving the correct stress, that's worth 2 points apiece. So this was just like having the equation written was 2 points. So we really try and break it down step by step and assign points all along the way. And if you've done a diagram like this, even if you don't have time to do the problem, you will get most of your points, okay? So it's a tip, take it for what it's worth, okay? I think for the sake of time, I'll work this one after class today, because we've already seen how heat capacity works. So I'm going to do it after class. It'll be in the notes, but we're going to move to, for right now, to band diagrams. Okay. Electrical conductivity is this fascinating property. When it comes to material science, it's unique. Why do I say it's unique? Because it has the biggest range of any materials property that I know of, right? As you look at different classes of materials, you could look at strength, and there's really weak materials like sponges, right? And really strong ones like carbon fiber or something. And they vary over, I don't know, a few orders of magnitude. But this varies over, what do I have here? 28 orders of magnitude. Just an enormous range, right? Remember, 9 orders of magnitude, that's a billion times. So this is like a billion times a billion times a billion. That's how much this thing ranges. It's astronomical how much these things range. You've got things like metals, like copper is a great example of a very, very electrically conductive material. So it's down here on the good conductor range. And you've got things like foams, glasses, rubbers that can be just massively unable to conduct electrons, right? And you've got everything in between. So why do we have 28 orders of magnitude difference? And what is the origin of this in different materials? Why is it that ceramics just don't conduct electricity? Why is copper so dang good at it? Let's dive into that. I think one of the easiest ways to describe that is with band diagrams. Okay? Band diagrams, while they're a little bit tricky up front, they make the rest of the analysis really easy. Okay? So band diagrams come about when you have more than one atom, right? One single atom, we could say what its electrons look like. Like start with like hydrogen. Hydrogen, if this is our lone hydrogen atom over here, it's got one s1 electron, right? And so you could write like you could call this the 1s1 energy level right there, and you could put one electron, right? It's not very interesting. It starts to get interesting when you bring lots and lots of elements, atoms, close together. As you bring them close together, right? Imagine you've got 2 here. When you've got 2, you could have written, like 2 of these 1s1 orbitals right next to each other. Let me draw that a little bit better, right? Both of those are technically 1s orbitals, and you could put electrons in them. But if you now are occupying at the same energy level, right? The y-axis is energy level. If you put all 4 of these electrons, let's say you had helium, so you've got 2 electrons each. If you occupy all of those 4 at the same energy level, then they cannot occupy the same volume. But if you see where these things start to get close to each other, and these electron sort of orbitals overlap the same volume of space, we are violating the Pauli exclusion principle. That is not allowed. Like, quantum chemistry does not allow that. You cannot occupy even a region of your same orbital, which is what they're doing here. Like some little pie slice is overlapping. You can't do that and also be at the same energy level. It's not allowed. So instead, what has to happen to fix this problem, if you're going to overlap even a little bit, then your energy levels can't be the same for the 2 different atoms, right? They have to split a little bit. Now that splitting can be tiny, right? It can be really small. As long as it's different, then we're not violating Pauli exclusion principle. So then let's say you bring a 3rd one in. Okay, well then you have to split those 3. How about a 4th one? And by the time you bring together a large solid which has a large number of atoms, you, instead of ending up with these big separations between energy levels, you end up with a continuous band. A band of energy levels. Now, if you take the total number of atoms, let's say you've got n number of atoms, then you still have n number of energy levels. It's just that the splitting between those levels gets so small that it looks more like a continuous band rather than discrete energy levels. Are there any questions about that? How a band forms in a solid? Okay? You bring atoms together, their shells overlap a little bit, and that leads to some band, right? Now, we're not going to cover it in this class, but if you bring them too close together, you can actually form band gaps, right? So you start bringing them close together, and these bands start to form, right? As your atomic distance, your bonding distance gets closer and closer, that's moving this way on the x-axis. So the band starts to form here. So you've got a band forming. At a certain point, you'll actually form a splitting of your bands. We're not going to describe why that happens in this class. So just take it as granted that for some, let's say this is your bonding distance, where it's thermodynamically favorable, you have a band where you can put electrons, you have a region where you cannot put electrons, and then maybe you've got another band where you can put electrons, okay? So this gives rise to two things. First off, bands, and then a band gap. So we're going to call this gap between where you can't put electrons, this one right here, that is the band gap. Right? Just think of it like, in terms of quantum mechanics, electrons are not allowed to reside at that energy level. They can be below it, they can be above it, but they can't be between. In fact, you can take things that are down here, pump it up with a little bit of energy, thermal, hit it with a photon, do things like that, and it can jump up to this state and temporarily occupy it until it relaxes and falls back down to that energy level. Because there's a difference in energy, you need something to promote it, and when it jumps back down, it's going to release that energy typically as a photon. Light's going to be given off, typically. It can also be a vibration, okay? Any questions so far on this, on band diagrams, on band gaps, on bands?
Is it the material that's not allowing the electron to be in that void?
It's quantum mechanics is not allowing it. And so why this void forms, maybe I'll prepare like a supplemental YouTube, but I'm not going to cover it in class today because it's a little bit lengthy. It's interesting, but it's beyond the scope of what I want to cover. We're going to keep electronics really simple in this chapter and mostly do diagram-based rather than nasty equations. Okay? So because you've got these band gaps that form in a material, this gives rise to why you have insulators, metals, and kind of metals. Right, semiconductors, right? So take for a minute a conductor like a metal. If this whole thing is potentially where electrons can occupy, in a metal, you're what's called a Fermi level, and this means the point at which you run out of electrons. Electrons are going to fill the lowest energy spots first, and they're going to fill up in energy, just like people on a bus, right? We have preferred spots to sit on a bus. We like to spread out. And then only when all the empty seats are taken, we start to pair up. That's kind of what's happening here. It's going to start to fill up, and eventually the bus is full if you get to the top of that. Well, metals, they don't ever fill up. The total number of electrons stops somewhere in the middle. Now, there's different colors, and that represents different levels of occupancy. If this was at absolute 0 Kelvin and the electrons had all their thermal energy sucked out of them, this would be at a hard flat line right in the middle. But because it's not at absolute 0, these things have some finite temperature, then some of these electrons might have enough thermal energy to jump up and occupy a slightly higher level, and that leaves empty spots down here. That's why they've chosen to show this as a gradient of color. It's just that it's not like a hard cutoff in energy unless you're at absolute 0. Or in other words, if I was going to sketch this, let's say I wanted to sketch energy, if I can get my pen to wake up. I don't know if I can. I'm going to have to switch it. Okay. I don't know why that works, but it drives me crazy. Okay, so let's say that we were filling up as a function of energy. Let's draw energy on the x-axis. Well, let's be consistent. We'll draw it on the y-axis. If energy is on the y-axis, and this is, say, fraction filled, right? Just call it F for now. If it was at absolute 0, we would have, if this was 100%, we would have it look like that. At a certain energy level, we would have 100% filled, right? But that's not what we're getting. Instead, we're getting this. We're seeing sort of a curve that looks like that, okay? Where some of your electrons can occupy a higher level and some at a lower level. I think I drew that backwards. I'm going to draw it the other way to make sure I get it right. We're going to draw our energy down here. And on the y-axis, we're going to put probability of occupancy. Right? So that's our probability of occupancy. So 100% would go to 0, right? That would be at 0 Kelvin. And then if we draw this at a different temperature, let's say like, I don't know, room temperature, it might look something like this. Where you took some of these things that were down here and now they've occupied up here, okay? And higher temperatures, it's going to start to look even more what we call a soft distribution. So like this might be like 1,000 K. Okay? Where more and more of these ones down here are going to occupy higher energy levels. Any questions on this? It's called the Fermi distribution. Any questions on that, on what's happening there? Okay, we're going to use that a little bit later. Okay, so that's in a metal. That's what the sort of gradient color is. So these would both be metals. In this case, it's a single band. In this case, you've got two bands that overlapped, and the average energy is still in the middle of empty seats. But now compare that to an insulator. In an insulator, you have just enough electrons to fill this thing completely up, right? And then you've got a completely empty band above. So if this band down here is full, and this one up here is empty, then you can't have good conduction. Think of it like people on a bus. Like imagine you're in England, jolly old England, you got the double-decker buses, right? If you're sitting on the lower level, because you don't want to walk up the stairs, because that costs energy, then people are going to eventually, they're going to fill up that lower level. And when it's completely full, there's no empty seats, imagine if you wanted to hop from seat to the back of the bus. Well, you can't do that because all the seats are filled. That make sense? You have poor conduction. You can't really hop from site to site. But if somebody gave you some energy and you climbed up the stairs to the top level of this bus, now you could hop from seat front to all around the bus if you wanted. Plus, by you going upstairs, it made an empty seat downstairs, right? On the lower end of the bus, and people can now hop from seat to seat as that vacant seat moves around. Does that make sense? That you make conductivity better in two ways. One, you put a person on the top deck where there's empty seats. We call that an electron in the conduction band. So this here is called the conduction band. So the conduction band is the one that had been previously totally empty. We now put an electron in the conduction band, and because that electron came from what's called the valence band, it's now going to create a vacancy in the valence band, or a spot where an electron used to be, and we call that a hole. Right? In physics 2, you guys learned about holes, right? Is this the first time you're hearing the term hole as an absence of electron? So it's just an absence of electron, right? If you have all the available spots for an electron, if those are all filled, then you have a valence band, which is filled with its electrons. If you take one of those out, now there's an empty spot where an electron could sit. That's an empty orbital where an electron could occupy. If we took one out, we call that a hole. Okay? It's just the absence of an electron. And both of those can conduct electricity. It makes sense why the electron conducts electricity. This guy can move around with a bunch of empty seats. And this one also conducts electricity because nearby electrons can jump into that empty seat and it can move about as well. Okay? Any questions so far on why, on this topic, I guess? So in order to jump up from here up to there, if you have a big difference in energy, if this band gap is really large, then it's going to be hard to promote this electron from here up to there, right? That means that it's not going to happen very often. So these are your insulators. If you have a great big band gap, like is often the case in many ceramics, you don't get good conduction because so few of your electrons are able to occupy this that you don't have many electrons now available to conduct electricity. Meanwhile, metals, you don't need to overcome any band gap. And then you've got semiconductors. Semiconductors are just like insulators, but the band gap is smaller. Something maybe on the order of 1 or 2 electron volts. If it's just a few electron volts, then thermal energy from the room, right, from its environment, can cause some of these to get promoted. See how they've drawn like a light pink here and a light pink here? That means that some of these electrons already hopped up there. So you created holes here, and you've got free electrons in that conduction band. Any questions on this? Simple as this is, this really explains semiconductors well. Okay? And there's lots of different ways of showing this. Again, they're showing with gradients here. Here's a metal. This is a type of semiconductor which is called a semi-metal. It technically means like there's almost a band gap, but not quite. You've got a P-type and an N-type semiconductor and a regular semiconductor. What's the difference between P-type and N-type? Well, the dashed line represents the point at which you have electrons if you were at 0 Kelvin. You cool it all the way down, where would the electrons like to fill up to? Right up to that dashed line. If it lies right in the middle of your semiconductor, then it's going to be symmetrical like this. If it's a little bit closer to your valence band, or if it's a little bit closer to your conduction band, then you get a P-type or an N-type semiconductor. P-type means that you're going to end up with extra holes here, but those holes don't make it all the way to your conduction band. They go somewhere else, which we'll describe in a minute. If it's N-type, it means that you have some extra electrons here, but they didn't come from your valence band. They came from somewhere else, which we'll describe in a moment. And then you've got an insulator, which means the gap is too big that you don't get anything happening. Any questions on this so far? Okay, so again, P-type means it has extra holes. And N-type has extra electrons. Normally you would think that it's the same number, right? Go back to our people on a bus analogy. If there was 20 people on the bottom level of a bus, one of them moves upstairs, then you have one free electron person upstairs and one hole in the basement, right, in the bottom floor. So they're typically equal numbers, but in P-type and N-type cases, they don't have to be equal. You can have only one type or only the other type for the most part, okay? All right. So, okay, here's our distribution. That distribution, you could imagine overlapping this, right? Since this is energy going that way, you could say that maybe your valence band cut off right here, and your conduction band was right there. If you get it hot enough, some of your electrons will occupy that conduction band. That's what they're trying to show in the picture below here. They've just tilted the axes. They've made energy on the y-axis again, and they're showing how you can get, if you get it hot enough, see right here, you get some of your electrons starting to occupy the conduction band by forming empty spots down here in your valence band. Okay? And we've got some examples if you want to watch more about that. Okay. So, group question. We've already talked about that one. How about this one? Clicker question will be, if you've got an insulator and a semiconductor, they're both at the same temperature, will they have the same electrical conductivity? Why or why not? All right, so let's go to that one. So I didn't actually program this one. So talk to your neighbor. If you've got an insulator and a semiconductor, the only difference is the band gap size. Should they have the same electrical conductivity if they're at the same temperature? Why or why not? What do you think? Okay, what do we think? Should they have the same electrical conductivity or no? Anybody feel brave on this day before the turkey bonanza? Nobody? How about in the red polo shirt? Remind me your name again. Red and white.
Aaron.
Aaron, what do you think, man?
I would think that semiconductors would have more electrical conductivity.
Correct. What's the rationale behind that? So think of energy like calorie, like we eat, okay? If you're going to run a really long race, you need a lot of calories, right? You need lots of food energy, right? So we're not talking about that with these things. They're getting most of their energy from thermal energy, right? But still, they've got to go up to get to that conduction band. They've got to jump from their valence band up to the conduction band. If that's a small gap, that's like running a short, like a sprint marathon or whatever it is, right? Where it's you don't need as much energy. But if it's a full marathon, you need a lot more energy. So that's the difference between a semiconductor, which has a small band gap, and an insulator, which has got a really big band gap. So if it's a big band gap, then that little amount of thermal energy may not be enough to overcome it. So even though they're both at the same temperature, you could convert temperature to thermal energy just by multiplying it by the Boltzmann constant. And basically, maybe 25 millielectron volts is enough to promote it across the small band gap, but not anywhere close to enough to get it across an insulator. So you'll have different number of electrons occupying that gap. Okay? So they will definitely not. Because somebody give me a one-sentence recap. Why is it not the same? Different band gap leads to what? Yep. Means more thermal energy required for one over the other. Okay? Any questions on this so far? Yeah. Carter. Yeah, absolutely. It absolutely does. So materials that have like a really big band gap, you expect them to have a really low electrical conductivity, and vice versa. Really small band gaps tend to have much larger. Okay? All right, there's something called electron mobility that we should talk about. Mobility has to do with as an electron is hopping, maybe from empty seat to empty seat, it can still undergo scattering events. Maybe it crashes into another electron or to an atom and it changes its direction temporarily, right? So the mobility, the electron mobility or the hole mobility, which is the ability for a hole or the absence of electron to move, we need to be able to quantify that, right? And really the best way to think of it is, like you'll see like these modeling experiments where they apply an electric field. They apply an electric field across this thing, and that causes a charged particle to move across it. Let's see, electrons move opposite the field, right? Yeah, if the electric field's that way, electrons move this way. So the electron might be traveling one way, but it might bounce into things, right? And so they've sort of simulated 4 different scenarios. In one case, it can travel an average distance maybe. Here, it's traveling a really small distance before it collides with something like an atom, an impurity, a grain boundary, a dislocation. So if they zoom in, you see there's lots and lots of these sort of collision events. This one, it travels long distances. It just hits these sort of precipitates that are in your material. So you can imagine that all sorts of things might scatter electrons. And so think of it like drift velocity. Well, the name is drift velocity. Think of it like terminal velocity. If you jump out of an airplane, gravity is acting on you for the entire time that you jump out of the airplane, right? So there's constantly a driving force for you to accelerate, right? Right? You agree? Like you should keep on speeding up because gravity's always there. It changes a little bit, right? Because it's a function of radius of the Earth. So like technically it's getting a little bit weaker as you jump, but it's always there. So why do people hit what's called terminal velocity, where they stop speeding up after a while? When you jump out of an airplane, you stop after a point. This is why you can drop an ant from like crazy heights and they don't die, because they reach terminal velocity and it's not enough to break their bodies, right? Whereas humans, our terminal velocity would kill us, right? So why? Why does terminal velocity exist at all? Why shouldn't you just keep on accelerating? You have a drag force, right? A drag force means you've got friction with the air around you, and sooner or later that force is going to be equal to the F equals ma force from gravity acceleration. And when they're equal to each other, it's not that you stop moving, it's just you stop accelerating. So you fall at a constant velocity, which is, I don't know what it is for humans, something, right? So electrons have something similar. If you apply an electric field across a device, that electric field, since it's a charged particle, it wants to be accelerated. But it doesn't just accelerate infinitely, because it undergoes a bunch of collision events, and that's just like friction. Think of it like electron friction is those collision events, okay? So if we wanted to quantify that, the maximum speed that an electron will travel, v sub d, that's our drift velocity, is going to be equal to the electron mobility, that's the Greek letter mu, times E, our electric field. Right? So for a given electric field, if you want to figure out how fast things travel through it, you have to know the mobility. And the mobility is just a function of the impurities in a material, things that would influence how many scattering events it has. So what things influence scattering events? Well, maybe thermal vibrations influence it, or impurities, or dislocations due to deformation. All of these things will add friction for your electrons that are moving through your material. Yeah, Ashton?
Typically, you want, is it a certain perfect temperature that electronics should be running at? If it gets higher than that, then the thermal vibration increase, which would decrease the speed of the electron.
Yeah, I think I've got it right here. So this is showing electrical resistivity, so it's resistance to electrical flow, as a function of composition of nickel. So this starts out pure something, and you're starting to dope it with nickel. And look what the resistivity is. The resistivity is going up, 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 because as you dope it, you're providing extra things that those electrons can scatter into, nickel atoms, right? Well, this same plot exists if this was temperature. Instead of composition, if this was temperature, as you heat it up, there's more and more thermal energy. And so if it's a metal, it will become more and more resistive as you heat it up. That's not the case with semiconductors, as we'll describe in a minute, okay? So Matthiessen's rule basically says, okay, there's all these things that add friction. You can add them up, right? The total resistivity is just a function of the resistivity due to thermal vibrations, plus the resistivity due to impurities and everything else, right? If you remember our demo from the iron wire demo, that piece of iron wire had a couple bends in it that I'd accidentally bent it a little bit. So instead of being like this nice perfect wire that was like that with no bends, there's a couple spots where it was like this, right? I'm like dramatically magnifying this, right? But if you noticed, and I don't know if you remember this, when I heated it up, it didn't turn orange all the same way. These things turned orange first. Why did they turn orange first, and then the rest of it slowly turned orange afterwards? Turn to your neighbor and explain what's going on there. Okay, what do you think's going on? Let me ask Jake. What do you think's happening here? Why is it that certain spots seem to heat up relative to everything else? What's going on, Jake? Yep. Or you could think of it like this. The rate of collisions, right? When they collide into something, that's what's imparting the energy. That's Joule heating, right? Is when the resistance is, when you have a resistance, it's going to cause heating. So let me ask you this. Is the resistance the same here as it is at that bent spot? Why might it be different? What's different about those two spots? Well, when you bend something, which one of these three things that we've listed, you got your thermal vibrations, you've got your impurities, and you've got deformation. Which one of those is probably contributing to the increased resistivity? Deformation, and that's because you've got things like dislocations. When you deform something, you cause deformations in the material, right? You fill it full of dislocations. So the more and more dislocations you have, those are going to be collision sites for your electrons. So this is going to heat up a little bit more than the stuff around it. So it's totally common to see like hot spots in your wire. And in fact, we once had one last week when I was doing this demo where it had a local hot spot that caused the wire to actually melt when I did that demo, just in that one spot, and actually melted and broke the demo, okay? Even though most of the wire was fine, I maybe bent that one spot too much and it locally heated up quite a bit. Okay, so when you want to calculate the overall electrical conductivity, we use this expression right here. The electrical conductivity, assuming we have a metal for right now. A metal means the only thing carrying electrical current are the electrons. Then the electrical conductivity, sigma, is going to be equal to n, the number of electrons, multiplied by the charge of that electron. That's the E with the brackets around it. That's our absolute value of the fundamental charge, multiplied by the mobility of an electron. Okay? So that's our expression for electrical conductivity. We're going to modify that in just a minute. Skip that. All right, let's talk about conduction in semiconductors. How are they different than conduction in a metal? A couple different ways. Let's start with an intrinsic semiconductor. An intrinsic semiconductor means that we haven't doped it. It's a pure material. So say something like pure silicon, right? Silicon, pure silicon, if you were to look at the band diagram, you've got the valence band, you've got the conduction band, and then the Fermi level, which is the level at which the electrons would like to fill. If it was 0 Kelvin, it's right in the middle. It's symmetrical. That's for an intrinsic semiconductor. So this could be something like silicon, but it could also be something like gallium arsenide, indium antimonide. So that would be a combination of group 3 and group 5. So they'll call these a 3-5 semiconductor. Even though it's not a pure substance, this material has the Fermi level right in the middle of the band gap. So it's still what we call an intrinsic semiconductor. And that just means it doesn't favor electrons over holes or vice versa. They're both equally present in the material. You could also have a 2,6 compound. So what are these numbers actually referring to? If we go to our periodic table, and we look at silicon to start with, silicon's right here. It's group 1, 2, and then it's got 3, 4, right? Silicon wants to bond with 4 other silicons. And so silicon forms 4 bonds with 4 other silicons, and that's how it reaches its rule of 8. But meanwhile, if you have gallium, which is right here, and arsenic, which is right here, that's a 3 and a 5. Or if you had indium antimonide, right, it's a 2, 6, and so forth, right? So these That's how you form these different semiconductors, is by trying to reach that total of 8 electrons. And these are all intrinsic semiconductors. Now, what are their band gaps? They're typically somewhere less than 2 electron volts. Silicon, for example, is 1.1 electron volts, right? 1.1 electron volts. Whereas germanium, it's 0.7, okay? As you move from group 4 elements to 3, 5, 2, 6, you're making it less and less covalent. Covalent means that they both are the same element and they have the same electronegativity, so they just want to perfectly share. If you've got, instead of that, a mixture of indium and gallium, or gallium and arsenic, for example, they have different electronegativities, so you're going to start to increase the degree of ionic character. And as you make it more and more ionic, it's a stronger bond. That leads to a larger band gap. A larger band gap as you make it more and more ionic. Okay? As I've said, intrinsic semiconductors have equal numbers of holes and electrons. Holes we write H with a little plus sign. That's just a missing electron. And there's equal numbers of those, as we've described sort of ad nauseum today. Okay? So let's start with a picture of our silicon, right? So if you've got silicon atoms, we said that each one of these silicon atoms, if you look at your periodic table, it's only got 4 of its valence electrons. It's got 1, 2, 3, 4, but it would like to get to 8. And the only way it can get to 8 is by sharing. So if this guy's got 4 electrons, I'm going to draw them with alternating colors, just to make it clear. And the one, its neighbor, has 4 electrons, right? The only way that it can get to 8 is by sharing. Or in other words, the bond is these 2 electrons being shared between those 2 silicons. These 2 electrons being shared, right? And so each one of these silicon contributes 4 and it shares with 4 others. And in doing so, you end up with 8 electrons and a filled band, right? The band is filled. This is why when we draw this thing with its band diagram, this valence band is completely filled in this structure. It has no leftover electrons, right? All of the electrons are tied up in the bonding that you would expect for this thing, right? If we were to finish this. All these electrons are tied up. There's nothing left over here. Okay? And in doing so, silicon ends up with its 8 electrons, so it's happy. That's why we call this an intrinsic semiconductor. We didn't have to add some other dopant or impurity to add electrons to make this work. Okay? Any questions so far? We're going to modify this, though, okay, in just a minute with extrinsic. If you wanted to calculate the electrical conductivity of an intrinsic semiconductor, it would look like this. It's different than the expression we just showed you previously. Now the overall electrical conductivity has 2 terms. It's got the term from your electrons, that's Ne times the mobility of an electron. But you also have to account for the holes, right? Every electron that gets promoted to the conduction band came from the valence band, and that created a hole, P. So you have to have the charge of electrons still, but now you have the mobility of a hole. And what's interesting, and we're not going to cover in this class, is that the mobility of electrons and holes are not equal. That's a little bit strange. That a free electron, when there's a bunch of empty seats, a person could hop from seat to seat at a different rate than if this was totally filled with students except for one empty chair. That empty chair, as it hopped, as students moved it, they don't travel at the same rate. That's a little bit strange. It has to do with having a different mobility. They experience different frictional forces, and we're not going to describe why in this class. Okay? Or in other words, N is equal to P, but these 2 terms are not equal to each other. The mobilities are not equal to one another, and so you have to treat them separately. And a spoiler alert is that the electron mobility is typically higher than the hole. It's easier for an electron to move than it is for an empty seat to move. Okay? Any questions? Any questions why we have to use this formula with 2 terms instead of just this one like we did with metals? Make sense? Okay. Let's keep going. So that's intrinsic semiconductors. Extrinsic semiconductors are ones where you dope it. You start out with the silicon, or maybe you start out with the gallium arsenide, or you start out with the indium antimonide, but now you're going to intentionally dope it in such a way that you move the Fermi level. Maybe you're going to add electrons, or maybe you're going to take them away. So if we draw our band diagram from before, it looked like this. And before, our Fermi level was right in the middle. Now we're going to either add or take away electrons, And in doing so, we're going to move the band diagram up or down. We would call this n-type if we move it up. If we move it down, then we're going to call that p-type. Okay? So what is actually going on here? Let's draw sort of a picture of this. So let's go back to our silicon example from before, right? We've got silicon, 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 silicon. Let's put a phosphorus. Let's put a silicon. So I'm just going to circle these. All right, those are our individual atoms. And silicon, just like before, it's got 4 electrons. So I'll sort of alternate these things. But phosphorus, if we look at it, how many electrons should it have? Phosphorus is right here. How many electrons ought it to have? It should have 5 valence electrons, right? So let's draw that. This one's got 1, 2, 3, 4, and then it's got this 5th one, right? So if let me just change the color so it's kind of clear which ones are which. This guy's got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. If we draw the bonds now, these two are in a bond, 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 bond. Those are all bonded up. And you could keep on going, and you would quickly find that something's happening, that one is not involved in a bond. The phosphorus, because it was that one extra, you don't need that one to get to your 8-electron rule. In fact, this ends up with 9 electrons. That's not desirable. It means you've got an extra electron, right? So phosphorus, it's going to have it's got, 15 protons and 15 electrons. So this is 15 protons. So technically it has 15 electrons, therefore those things are attracted to each other. But this thing's not held very tightly. You can strip away that electron with a little bit of effort. It does take energy, right? Because it's 15 electrons, you want to have the same number. And if you take that away, then you're only going to have 14 electrons, which doesn't balance with the 15. So that does cost energy to take this thing away, but it's not very hard to take it away. So you've added an electron. Or in other words, you started out with your Fermi level in the middle. By adding electrons, you moved it up, right? Or another way to think of this is that you've got a band where this is your phosphorus atom. And the electron, let me change its color so it's a little clearer. This extra electron, we'll draw it in green. That electron could be promoted to the valence band, or to the conduction band, with only a small amount of energy. Because that phosphorus doesn't really care if it loses it, because it already reached its rule of 8 thing. It doesn't really care if it loses that electron. So it doesn't take very much energy for that to happen. Therefore, we draw this gap as being really small. Does this make sense? The band gap has not changed. But we've introduced an impurity that, in effect, has a really small band gap, you could say. Any questions on this? Okay, what if we wanted to go the other way? What if we wanted an excess of holes rather than electrons? What would we do? Well, let's go back to our periodic table. And you'd say, okay, now we want something that's going to accept an extra electron. So instead of having 5 instead of 4 electrons, let's pick one that has 3, right? So go to the left. So something like aluminum or gallium, something like that. If you dope silicon with a little bit of aluminum, imagine how it changes our picture, right? It's just like before, so forgive me, I'm going to draw this though. You've got your silicon atoms, right? Silicon, 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 silicon. And now you're going to draw your aluminum atom. And aluminum, it's only got 3 electrons, right? So if we draw our electrons from our silicons, this guy had 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. This one had 1, 2, 3, 4. 1, 2, 3, 4. Okay, let's start drawing our bonds. You've got a bond, just like regular. But what you're missing right here, you're missing an electron for that bond to form. That make sense? Like that thing it's not satisfied because it didn't reach its rule of 8. Therefore, this is an empty seat. This is a vacant seat. Right? And because of that, a nearby electron, say this one, it could hop down there and occupy that seat, and that vacancy would travel up to there. This makes sense? So because of that, you can still have electron motion in either scenario. In one case, it's hopping to fill this empty seat, and in the other one, in this case, it basically moves to another orbital, which is just called the conduction band. It's a completely different band, and it's able to freely move through the material. Any questions on this, on extrinsic semiconductors? Yeah, Rory, or is it Bryce? Rory.
How much does like the size of the impurity make a difference?
The size of the what?
Like the impurity.
Oh, good question. The size does matter, because if you, say, take an electron, or something that's way, way too big, it won't substitute at all. If you take something ginormous, it just won't be able to fit on the silicon site. That would be a problem. And if you have one that's a little bit bigger, it's still going to influence it because it will strain the nearby lattice. And strain is going to influence electrical motion. It's going to cause them to have more collision events. Okay? Other questions on this? This is definitely a question that will be on homework and final exams. Something related to band diagrams, being able to sketch them for a p-type and an n-type, and explain what's happening here. So again, if I was going to draw the aluminum here, the aluminum would look something like this. That's our aluminum atom, right? Where an electron down here could hop into that seat and create a vacancy. Okay? So we call these donors or acceptors. Phosphorus would be an example of an electron donor, and aluminum would be an example of an electron acceptor, right? What else can I say about this? We already drew that. Okay. There's no corresponding hole create. Okay, yeah. This is important. The reason that we can end up with more electrons or more holes, right, and not just equal numbers of both, is because this extra electron from phosphorus, it was proportional to how many phosphorus atoms you doped into the material. If you add 1 in 10 phosphorus, you know exactly how many extra electrons you're going to get. But you're not going to create vacancies in this lattice, right? All these bonds, there's no vacant site on there like that, because you started with an extra electron to start with. Meanwhile, down here, it's the same thing. Every vacancy, that tells you how many holes there are. So they're not equal numbers, okay? Because of that, you have something called your intrinsic carrier concentration. Intrinsic carrier concentration is just N and P being equal to each other. So in the case of an intrinsic material, that's from thermal vibrations. It jumps all the way from the valence band up to the conduction band. There's some number of electrons that will always do that. It might be really small, but there's some number. But your extrinsic carrier concentration is typically far, far larger than that because you dope it with a large number of these extra dopant atoms, right? So if you dope it to be N-type, then you know that the number of electrons is going to be far, far larger than the number of holes, which is just equal to your intrinsic number of electrons, right? And because of that, you can modify this expression to look like that. Before we said this, that conductivity was equal to the number of electrons, the charge of that electron, the mobility of that electron, plus the number of holes, the charge of that hole, and the mobility of your hole, right? But they basically said that because N is so much larger than P, we can only look at that term and we can ignore that term. That's what we're saying here. If it's N-type. If it's P-type, it's the other way around. You only care about that term and you can ignore this term. Any questions on that? You're always right to include both terms, but when you dope it, it's so much larger. If this was like 1 million and this was 1, well, 1 million is still basically equal to 1 million and 1, right? It's no, you can ignore the 1 term because it's so small in comparison. Okay? We are out of time. We'll pick up here next time on how temperature plays into semiconductors.